today, I'm going to finish 6.5. In time permitting, I decided to pick a relatively recent Chapter 6 test. So I'll show you the 2023 Chapter 6 test, okay? Version 2 if any. But that presumes we could finish 6.5 first. So last time we met, we talked about how do we decide if the molecule is polar or not. Well, first, are the bonds polar? If they are, the molecule might be, either because of shape or composition. If the bond dipoles cancel, then the molecule will be non-polar. If there are no bond dipoles there anyway, the molecule can't be. And based on the number of shapes we went through, it might at first glance seem like a tall order to predict which molecules are going to have bond dipoles that cancel or not. Well, the answer is really, is the molecule symmetric? And we started with a very simple assessment by saying, let's pretend that all the x's are the same. And if we look at all of the AXN, EN notations, we discovered, and if you look on practice problems specifically, on the top, '41. There's 4 vertical columns. The 2 vertical columns on the left are relegated to the symmetric molecules where the bond dipoles, if they're there, cancel, meaning the molecules will be non-polar. And we kind of went through it. If there's no E's on the central atoms, AX2, 3, 4, 5, and 6, and all the X's are the same, any bond dipoles that are there will cancel. Get the first one for you. AX3 is triangular planar. All the X's are the same. Bond dipoles cancel. AX4 is tetrahedral. Same thing. AX5, trigonal bipyramidal. Symmetry. Bond dipoles cancel. AX6, same thing. And then there's 2 AXMEN notation where we do have lone pairs in the central line. But even if the bonds are polar and the lone pairs are there, the molecules are still symmetric. One of them is AX2E3, which is linear. And remember, 5-coordinate system, equatorial and axial. Lone pairs always go equatorial. If there's 3 of them there, all we see is a linear structure. If the x's are the same, molecules not there. And the other one is AX4E2. All of the other AXMEN molecules, all of the ones that have lone pairs on them, if the bonds are polar and the x's are the same, the bond dipoles don't cancel. The molecule will be polar. Okay. Now this represents simplified version of the table you're eventually going to see on the sample test I'm going to throw up near the end of the period. All we do is central up. That's AX3. Now, if all the x's were the same, it would be a non-polar element. But obviously they're not. In that triangular planar structure, carbon is going to pull electrons into hydrogen, oxygen is going to pull electrons into carbon. So the bond dipoles will reinforce each other. So it's not shape now, it's composition. So the molecule will be polar. It will be polar here too. AX3E, that's triangular or trigonal pyramid. Nitrogen pulls away, oxygen's away, or that electrons away from hydrogen. It's a pyramid. So the bond dipoles reinforce each other. Overall. Here, no. That's AX5. All the X's are the same. And when we draw this, just a quick reminder as to how to draw these things. Notice there's no attempt to make this thing look 3D. This one has to be. I have to be, what's pictorial and what's actually. Those, here's the two axial. One of the equatorial positions is in the line. One of them comes out of the board. You draw this like that, sort of put that bond in front of that circle, so a little easier to see. And then the other equatorial position is that's trigonal like now I can tell like that equatorial. This designation is something we're going to use often in organic physics. And that would be your opinion. Now let's talk about the type of intermolecular forces that results from shape. To get an idea. You've seen that opposite charges are ultimately responsible for electron deficient cations are attracted to electron abundant anions in a harmonic bond. And pairs of negative electrons are attracted to adjacent parts of the mutually available. We know. But these are chemical bonds. If they're within molecules, we call them intra. Chemical bonds within molecules are intra, meaning within or inside. And attractive forces between molecules and between ions and molecules. And we're going to talk about three forces between neutral molecules, and then one between molecules and ions. Inter, between molecule forces, are as dependent on electrostatic attraction as intramolecular. But between molecules, they typically involve smaller charges and or greater distances, which means intermolecular forces are never as strong as chemical bonds. Yet it would be incorrect to conclude, therefore, that they're less important than chemical bonds. Our final discussion of this chapter then will focus on the various types of intermolecular forces that exist. Begin with the forces acting between molecules, and then consider an important force that acts between molecules and ions. All equally important. So let's start where our previous discussion ended by revisiting polar molecules. The example of a simple polar molecule, we chose hydrogen chloride. Bond is polar, there's only two atoms in a molecule, so the molecule is with a chlorine end based on its electronegativity of 3, the hydrogen end based on its electronegativity of 2.1, definitely has more electron density than the chlorine side. And if it's only a 2-atom molecule, obviously it has to be linear, there's no shape issue, the molecule has to be polar. Within any substance containing polar molecules, each molecule has a positive and negative pole, not a charge, just more electron density on one side, less electron density on the other. We call it a molecular dipole, and chemists actually can quantify that. And you don't have to know this, but the term is dipole moment. Because of these partial charges, the the molecules in the liquid and solid phases. We call those the condensed states of matter because the molecules are touching each other. In the liquid and the solid phases, polar molecules will naturally orient themselves so that the positive pole of one molecule will be next to and attract the negative pole of an adjacent molecule. This force of attraction is called, as you might expect, dipole force. One molecular dipole and another. And here's two ways to represent it using the hydrogen chloride molecule. So the chlorine end is the more electronegative. The hydrogen end is the more electropositive. Notice I've drawn the chemical bonds within the molecules are solid bonds and shorter than the intermolecular force between the molecules. Longer and has some dash. That's one way to represent the dipole. Here's another way. That's similar to a little bit negative, a little bit positive. Electronegative end for this molecule is positive, negative, oriented, attractive, electropositive end of this one. Again, longer dash. That's a generic dipole force. A much stronger example of a dipole. We don't even call it because it's that much of a difference. It's called a hydrogen bond. We use the word bond, but it's not a real bond. It's just a reminder to ourselves that it's much more intense than a regular dipole. A much stronger example of dipole force exists between polar molecules containing hydrogen bonded to nitrogen, oxygen. It has to be hydrogen stuck to nitrogen, hydrogen stuck to oxygen, or hydrogen stuck to fluorine. Wow. The atoms of these second period elements are each small. Remember, as we go left to right, atoms get smaller. So the smallest atoms in the second period that take part in chemical reactions and have the third, second, and first highest electronegativity are nitrogen, oxygen. They're all small. They're all highly electronegative, 3, 3.5, and 4. They all have lone pairs. All of these properties are significant. The hydrogen nitrogen, hydrogen oxygen, and hydrogen fluorine bonds, and each of these molecules will be very polar due to hydrogen's low electronegativity, resulting in a large delta. This means that a significant amount of electron density will be removed from hydrogen. Remember, hydrogen only has one electron. So if we pull its only electron away from it, there's no core electron. As hydrogen has its electron cloud pulled away from it, we almost have an unshielded nucleus, which means something that's the negative end of a neighboring molecule can get really close to that almost unshielded nucleus. This will also leave then its nucleus almost unshielded because hydrogen has no core electrons. It's like one electron. The other end of the molecule will gain that electron density and thus acquire a large partial negative charge. The partially positive hydrogen in one molecule will then be attracted to the lone electron pair of the partially negative atom of another molecule, whether it be nitrogen, oxygen, or fluorine. That attractive force will be particularly strong because of the extreme polar bonds, but also all of the atoms are small. And the smaller an atom is, the closer something else can get to it. And the length of that attraction is very important. This allows the tiny electropositive hydrogen to get very close to the lone pairs of the partially negative nitrogen, oxygen, and fluorine in adjacent molecules. This intense intermolecular force is known as a hydrogen bond. I mentioned hydrogen bonds before. It's not an exaggeration to state that hydrogen bonds make life possible. For example, Consider that most of our Earth and most of your bodies are composed of water. Water molecules have a relatively low mass, 18 grams per mole. And the vast majority of substances composed of such molecules, even if they're polar, have very low boiling points, which means at very low temperatures, the compound exists as a gas. Figure 659 showing the boiling points of the binary two-element hydrides. In other words, hydrogen stuck to another element in groups 14 to 17. Now, it's kind of difficult to interpret this, so I'll help you. So here's the binary hydrides in group 14. Tin, germanium, silicon, and carbon all have 4 valence electrons. If they share all 4 of those valence electrons with hydrogen, we have binary hydrides. All of these molecules are AX. All of them are tetrahedral. All of them are symmetric and have the bond dipoles, if they're there, canceled. Notice that as we travel up a family, atoms get smaller. So this molecule is bigger than this one, which is bigger than this one, which is bigger than this one, which should suggest that the bigger a molecule is, even if it's non-polar, the higher the boiling point. And that kind of makes sense. It will make more sense in a few minutes. Suffice it to say that a big molecule is moving slower. The outer electron cloud is held less tightly. That usually means the boiling point's high. But it's not a high boiling point because even that one is like about minus 80 degrees Celsius. And it goes down as the molecules get lighter. We would expect that. We don't see any exceptions. But let's look at group 15, nitrogen. There's antimony, arsenic, phosphorus, and ammonium. All of these are AX3. Okay. As we travel up the family, atoms get smaller. Electronegativity increases. They're all of these structures are trigonopyramidal. They're not necessarily all polar based on the difference in delta En, but they're all asymmetric. So once again, we see boiling point drop. But then something happens between phosphorus trihydride and ammonia. If the trend were consistent, ammonia's boiling point would be about here. But it's not because of hydrogen bonding. If we look at group 17 halogens, HI, HBr, Cl, and again, notice the trend. It doesn't continue. HF way up here. Hydrogen bond. But the most important and most dramatic difference is in group 16. Oxygen is really H2PE, AX2E2, H2SE, AX2E2, H2S, AX2E2, polar, dipole dipole. All of them are the same shape. If the trend was to continue, water's boiling point would be about here, at about -90. But after sulfur, it would be way up. That's hydrogen. The group 14 hydrides are all symmetric AX4 molecules and non-polar, so we would expect that those substances are likely to have low boiling points. Note that the boiling points of these compounds decrease with decreasing molar mass. The binary hydrides of the remaining groups, however, are asymmetric, polar. Their dipole-dipole forces contribute to higher boiling points than seen in group 14. Something very interesting occurs, though, with the lightest hydrides in groups 15, 16, and 17. Nitrogen's group, oxygen's group, and it has nitrogen, oxygen. Look at how the boiling points change for hydrides as we move up each of those groups. Consider the group 16 binary. All AX2E2. Finally, as the mass of each polar AX2E2 molecule increases, one drops, not consistently. After H2S, if the trend were consistent, we would expect water to have a boiling point of about -90. The fact that the actual boiling point is almost 200 degrees higher is clear evidence of the strength of hydrogen bonds. Life as we know it would be variant if water became a gas at -90, given that most of the earth is covered with water, and most of what you're made up of. Even the fact that ice floats is due to hydrogen. Think of it. When water freezes, the ice doesn't sink, it floats. Because if you Google computer-generated diagram of ice, you have big hexagonal spaces all the way through the ice crystal. That's how the hydrogen bonds orient themselves. So that's a water molecule. A hydrogen bond between a neighboring water molecule would form at this lone pair and this lone pair. And that means that, and even if the ice forms slowly, it's even more of a pronounced effect. Those spaces mean the density of the ice is less than the liquid water. There's more space in the crystal than there is in the liquid. So they float. Ice is nature's styrofoam. It prevents convection. It keeps the water underneath the ice at a livable temperature. Imagine what would happen every year when winter came and ice sank. If it sank, everything in the river would die. But it doesn't do that. The significance of hydrogen bonds is further demonstrated by the fact that the three-dimensional structure of many proteins, which dictates a lot of how proteins behave, like hemoglobin, and even the base pairing of the double helix of DNA depend on the existence of these essential forces. So why does thymine always bond to adenine? Because that's how the two hydrogen bonds line up. There's a nitrogen hydrogen bond here and an oxygen hydrogen bond there. And for guanine and cytosine, there's 3 of them. Okay. And again, this is in 2 dimensions. There's a hydrogen bonds between one. There's the oxygen, there's a hydrogen. That dashed line is a hydrogen bond there. Between one of the lone pairs and oxygen, there's another. So those are the 2 forces associated with polar bond. Dipole, generic polar molecules, and much more intense hydrogen bonds. For a molecular substance to exist as a liquid or a solid, because we can't see molecules, the molecules must somehow be stuck together. So when I turn this on, obviously, if I see something, that means water molecules must be stuck together. This means some kind of intermolecular force must exist between anything that exists as a liquid or a solid. So far, we've discussed 2 of these intermolecular forces. Dipole forces and hydrogen bonds act to cause polar molecules to stick together, maintain a molecular substance, depending on the temperature in the liquid or solid state of matter. However, we might expect that substances composed of non-polar molecules, where the bond dipoles either aren't there in the first place, or if they are, they cancel each other out. We might expect that those substances never exist as liquids. There's no particular reason for the molecules to want to attract each other. That's definitely not the case. Many molecular substances composed of non-polar molecules exist quite happily at room temperature as liquids or even solids. Those that don't can usually be condensed or solidified in the right condition. The halogens. The halogens, apart from being the most reactive elements in the table, they are unique in that they exist in the three states of matter. But every halogen is diatomic. F2, P2, Br2, I2, AT2. That's the most radioactive. Any diatomic molecule with two identical atoms stuck in it has to be non-polar. So we expect fluorine to be a gas, and it is. They don't stick to each other. Same with chlorine. Being notice is great. That means it's a non-polar molecule. Yet how does it liquid at room temperature? Why would it want to stick together? Iodine's its quality. Why would that one stick together? So is acetate. So there's got to be some reason that these things want to stick together that isn't a result of dipoles, at least permanent dipoles. What intermolecular force would cause non-polar molecules to attract each other? Physicist Fritz London used quantum mechanics to explain the attraction. That should be. Let's look at a chlorine molecule. Obviously, if we do the Lewis structure, we assume those electrons spend no more time near one nucleus than the other. It's built in the end to zero. So let's say that that represents the electron you're following. Remember, in Lewis structures, you represent electrons across the nucleus. The charged particle weight governed by the laws of probability. As delta En equals zero, the molecules are nonpolar, and the electron density in the negative cloud surrounding the two molecules is evenly distributed, which means, on average, the electrons will spend no more of their time near one nucleus than the other. There's no bond dipole. The molecule can't be polar. However, laws of probability apply to electron behavior. In any individual chlorine molecule, the probability of electron density being unevenly distributed is very, very low. Let's pick a probability. Let's say 1 in 10 to the 20th. But then think of macroscopic samples, for example, or gas, where we've got unimaginably large numbers of molecules. If the probability of one of those bond non-polar bonds is found, if the probability that experiencing those electrons will be more close to one nucleus than the other is infinitely tiny. The fact that we're looking at lots of molecules means not only is it possible that at any instant in time, one of those molecules could possess an instantaneous dipole. Not only is it possible, it's likely with numbers that big. If it's likely, then an instantaneous dipole in one molecule could have an effect on a neighboring one. If the molecules are close enough together, it's completed and moving slowly. However, at an instant, there is a possibility that there may be more electron density at one side of the molecule than the other. So if you do instantaneous molecular dipole, it doesn't have to exist in length of time, it's just instantaneous. The dipole will have little effect on any other chlorine molecules that are far away. If those molecules are in close proximity and moving slowly, now how would we accomplish that? Say we got a gas. How would we get the molecules closer together? Well, pressure. How would we slow them down? Slow down molecules. Dry ice, warm or cold? Pressurize it, lower the temperature. Get closer together, and they slow down. Even a short-lived dipole in that scenario, in one molecule, will distort or polarize the electron cloud of a neighboring molecule. This happens because the negative pole of the instantaneous dipole will repel electron density in a nearby electron cloud to the opposite side. As well, the positive pole will pull electron density to the near side of a neighboring molecule. Every time that happens, every time one dipole induces another dipole, that induced dipole is going to induce another one, and another one, and another one. And in an instant, those dipoles will disperse throughout the sample. So here's an example of that. Let's say this is two chlorine molecules. Notice electron density is evenly distributed. But in an instant, we've got an instantaneous dipole here. You got a question? Do you always have to do that in that time? Or here's some, go ahead. Here's an instantaneous dipole. If another molecule was close to this positive, that's going to induce a dipole in this thing. And if this instantaneous dipole induces another one here, then we have an attractive force. And then this dipole is going to cause another one, and another one, and another one. So that instantaneous dipole will disperse throughout the entire sample. It won't last very long, just like my battery, it's a POS computer. But because it's always happening, there will always be attractive forces, even between non-polar. And the correct term is called dispersion forces, or London dispersion forces. And whether a molecule is polar or not, it's always there. This battery lasts about 90 minutes, fully charged.
What's the significance of the dispersion force? Like,
Significance?
like, but if there's so many molecules, like, in a concentrated area, like, what would even happen?
Molecules are going to want to stick together, even if they're non-polar,
But-
because of quantum mechanical nature of electrons.
Or would that only last for like an instant?
Well, any instantaneous dipole is going to last for an instant, but it's going to cause other ones, and other ones, and other ones, and one will disperse throughout the sample. But because we've got so many molecules, there's always instantaneous dipole. Again, based on probability, which means they will always be there. The instant that the battery dies, that means everything is yours. And it's going to ask them if I want to visit the stage. Bill, going to have to start from scratch. And then go. Yeah, 1% of the page. It doesn't really explain what did you do? Receivers. Connection to the circle. Although London forces are the only force acting between nonpolar, they exist between all particles, all substances. So even if there's dipole there, there's still London. Even if there's hydrogen bonding, there's still London forces. Except in the case of strong hydrogen bonds. the dispersion forces may be the dominant intermolecular force, even for polar molecules. Now, why would the London forces be particularly strong? Well, the strength of dispersion forces will increase with the size of molecules and also with the surface area. And again, let's quickly go back to the halogens. Let's pick the smallest halogens. Chlorine's a tiny atom. Imagine a peanut. Peanut's kind of the right shape. So let's say there's a peanut. Okay? Here's the chlorine. Let's say for an instant we do get a dipole. Well, because the electron cloud is held so tight, the only way that a dipole in this molecule will form another electron cloud of a neighboring fluorine is if they're really, really close and going really, really slowly. But even then, it's not easy because the electron cloud is held so tight. That's why fluorine's a gas. But if you travel down the halogens, fluorine's also a gas. Fluorine's a liquid. Iodine's a solid. So let's say that's fluorine. This is iodine. Much bigger electron cloud. Why is the cloud big? Because the other electrons aren't held tightly. Chicken or the egg. So with iodine, an instantaneous dipole in a big, loosely held cloud of electrons in one iodine is going to be able to quite efficiently to form another. Think of a big water balloon. Easy to change the shape and get that electron cloud distorted. Let's say this. That's why iodine at room temperature, the dispersion forces, even though the molecule is not full, is sufficient to make it a solid at room temperature. And if we travel down the halogens and compare their melting and boiling points, melting points are always lower than boiling points. That makes sense. So here's fluorine. Melting point, boiling point. Very little reason for those things to stick together. They do. It's just that not easy. Okay. So they don't turn into a liquid until they're colder than minus 200 degrees Celsius. They don't turn into a solid until they're below about 230 or 240. Very little reason for them to stick together. Chlorine, higher melting point, higher boiling point, but still well below zero. Then bromine, its boiling point is about 50 or 60 degrees. It's a liquid at room temperature. Changes to a vapor quite rarely, but London dispersion is enough to keep it a liquid at room temperature. And it doesn't melt until it's over 100. It doesn't boil until it's almost 200, even though it's a non-polar molecule. And iodine, because it's a non-polar molecule, we have an open container of iodine, it's solid, just getting bombarded with molecules in the air will often sublime. It'll go from a dark purple solid to a purple gas. But it wouldn't be a solid were it not for London dispersion. And then astatine, which is radioactive, most chemists have never seen astatine. It's like an ounce on the entire planet. Obviously, a much higher melting point. So that's as clear evidence as you could find. And halogens are a good example because all three states of matter are represented, but all of them are non-polar molecules. The only intermolecular force is dispersion. Okay. So, dipole, hydrogen bonds, dispersion forces. Those are between molecules. The last one we're going to talk about are ion dipole forces, which kind of get an idea of what's involved there. Dipoles attracting ions. We'll conclude our discussion of intermolecular forces by focusing on an important interaction that occurs when an ionic compound dissolves in water. Ionic compounds, as you all know, and as we demonstrated, all ionic compounds are below temperature because chemical bonds extend in 3 dimensions, holding the ions together. They all exist as ordered structured solids called crystal atoms. There's 2 ways to get these ions apart. Melt it, which is at a very high temperature, pulls the ions apart from each other. It doesn't separate them physically, it just allows them to flow as a liquid. And that for sodium chloride, it's 801 degrees Celsius. The other way to pull the ions apart is throw it in water. And water is uniquely constructed to pull ionic compounds apart. Water is sometimes called the universal solvent. So let's think of what happens when you throw this in water. On the surface of every lattice there are cations in it. It's in a water environment. The electropositive end of the water, the hydrogen, is going to naturally be attracted to the anions on the surface. They're going to surround it. They can't help it. The hydrogen electropositive ends are going to surround the anions. And if the attractive force between the molecules, polar molecules, and the ions, ion dipole forces, exceed the attractive force of the ions to other ions in the crystal, then that ion will be pulled away from the surface. And as it's pulled away, it gets wrapped in what we call a hydration shell. It's a little cage. So when I write, and you've seen this notation many times, when I write this, that really means it's the ions that are talking. So yeah, I know that. There's what that little AQ means, each of these things are wrapped in a hydration shell. We call it a hydrated ion. That's the anode. It's going to diffuse away from the crystal, exposing more anions to attack by water molecules and green carbon. What about the cations? Well, the cations are positive. So the water also has a negative. The oxygen is naturally going to be attracted to the cations in the crystal. Same thing. As those cations diffuse away from the surface, they themselves are wrapped in a little hydration shell. I've said a bunch of times that most of what you are is water, but not the pure water. It's a solution primarily of sodium chloride. A healthcare professional will call it normal saline. So it's not just water, it's a conducting solution that has sodium ions in it and chloride, among other ions. Were it not for that, and it's not just sodium ions, there's some potassium in there, some other ions. Were it not for the mobile ions, that fluid portion of your body could not conduct electricity. That's how nerve impulses work. They used to teach this in grade 12 biology. I don't think they do it anymore. But the biochemistry of a nerve impulse is pretty cool. The spaces between the neurons, you guys know what you call that space? Well, a synapse. And for an electrical signal to travel, there has to be a voltage difference between the end of one neuron and the end of the other. So what the body does is it exerts energy to pump ions across a membrane called active transport. And sodium and potassium pump is one of the things that is discussed. And as soon as those ion concentrations change, now there's a voltage difference. And that happens in an instant. And that's how the nerve impulse travels from here to here. Move your hand. Think, feel, breathe. All of that is nerve. That wouldn't happen were it not for the polarity of the water molecule and its unique ability to dissolve ionic compounds. So, at the center of one type of hydration shell, the negative oxygen ends of water molecules orient themselves next to and surround a cation. At the center of another shell, an anion is engulfed by water molecules oriented with the positive hydrogens, positive-ish hydrogens, next to the ion's negative charge. Now, this is only in 2 dimensions, but you kind of get the idea. So there's a hydration shell around the sodium. This one's better. There is a hydration shell around the chloride. Now, not all ionic compounds are really soluble in water. Every ionic compound is a little soluble. Sodium chloride happens to be particularly soluble. If an ionic compound doesn't dissolve that well in water, all it means is that the attraction of the ions to each other in the lattice is stronger on average than the attraction of the water molecules to the ions and cations in the surface. Okay? But there's no such thing as an ionic compound that is insoluble. Some ionic compounds dissolving always happens. We call that an ion dipole. Figure 6.5.13 shows the ion dipole forces acting through water and sodium chloride in an aqueous solution. Ion dipole forces are the primary forces responsible for the solubility of ionic compounds in water. That's the most important application of ion dipole forces. And aqueous solutions of some ionic compounds are almost as necessary for life as water itself. So the combination of water and ions makes a conducting solution. Ions can't flow, solutions can't conduct electricity, and you're alive because that happens. So we keep discovering reasons that without water, life is very unlikely. And think of all the chemistry attached to water being able to stick to itself really well. Think of how life on Earth wouldn't even be here at all if water had a boiling point of about -90. Yes?
Since there's no such thing as like a non-soluble, like does it just take longer for the crystal
No,
to
it's
break
just
down?
if you take Chem 12 next year, you have to take Chem 12?
Yeah.
Okay, one of the topics we talk about is solubility of ionic compounds in solution, solubility equilibrium. So very little of it dissolves before the rate of dissolving equals the rate of crystallization. So for example, silver chloride is not very soluble, but there are still some ions in solution. It's just not many. But there's no such thing as an ionic compound that doesn't dissolve at all. Sometimes, in terms of what you could see, it doesn't look like there's any ions, but absolutely. Now, we're done. 6.5. Don't worry about valence bond filtering. If you want to read about it, particularly if you plan on going to post-secondary chemistry, which you might, feel free. It's not difficult. You might wonder, for example, let's say this is carbon tetrachloride. Carbon has 4 valence electrons, right? 1s2, 2s2, 2s2. Choice is 4 valence electrons. Look at the bond angles here. 109.5. S orbitals. P orbitals. Right? Any of those facing at 109.5. The orbitals are all 90. The s orbital doesn't really have a direction. So how do we get valence electrons facing this direction? And notice that these 2 electrons are paired. And they're those are carbon's 4 valence electrons. How do all 4 of them get dissolved in bonds? Well, one way to suggest your reason is something called valence bond theory, hybrid orbitals. All of these bonds, all of these valence electrons are identical. In that molecule, there's no s orbital or p orbital electrons in the carbon. Imagine all 4 of those electrons being thrown into a mixture and 4 bonding electrons being spit out at 109.5. Each of those orbitals is 1/4 s, 3/4 p. We call it an sp3 hybrid. And there's 4. So there are no S2 or strictly P electrons in that molecule. There's 4 valence electrons that are 1/4 S, 3/4 P. And that's one way to think about hybrid organisms. You don't need, there's some example of hybrid organisms. But you own the book, feel free to read about it if you want. I don't know why Lionel left it in there, but he did. Whatever. Okay? Now, I'm going to stop there for chapter 6. You don't need to know anything beyond what we just did. The time constraints that I am consistently forced to operate under, as I've said, means I don't have time for chapter 6 testing, which may or may not be good news depending on your perspective. But I feel it incumbent upon me, although I can't afford 3 classes to have a review class to test to go through a mark test. I can afford a portion of 1 class to go through a past chapter 6 testing.